Number one, welcome to Chapter 3. This will be a one and done lecture. We'll be doing all 30 some slides in one. This is usually done in a single class. I did it today, for example, in one of my classes. And what we want to do is discuss the properties of water and how that relates to life. So with that in mind, let's remind ourselves that a river cuts through rock not because of its power, but because of its persistence. It takes time for the river to cut through and carve out gorges and valleys. Like it will take time for you to master the material. You got to put that time and effort in and persist through it. Okay, so as we walk through this, guys, as always, lists of objectives are always placed here, so you know what it is you definitely have to know and be able to do for my classes. So what we're going to begin with is just kind of go back and talk about that because of hydrogen bonding, the properties of water exist. Now, how do the hydrogen bonds get here? Well, it's because water molecules are inherently polar compounds. They're formed by polar covalent bonds. And when this happens, the polarity of water, because there's electron pairs sticking out of the oxygen end of a water molecule, and there will be positive ends sticking out of the hydrogen ends. So there will be the partially negative oxygen, the partially positive hydrogen, forming a polar molecule or compound. It is from a polar covalent bond. The oxygen molecule, being polar, has these two ends. And what's going to happen is they're going to result in hydrogen bonds, which result in these 7 things here. One might say polarity does not result from hydrogen bonds. It's, in fact, hydrogen bonds result from polarity. But these are the things our book. So majority of these are there because of that. I always kind of want to go back through my notes every now and again and just tweak them a little bit. And those are always old things I tweak constantly. I'm like getting the numbers right or getting some things where I've updated and forgot to add this, that, or the other thing. But we'll talk about cohesiveness. We'll talk about how it moderates temperature. We'll talk about how it expands upon freezing and also floats when it's a solid. We'll talk about it being a very good versatile solvent. We'll talk about it being very good at being fluid. It's a fluid over a wide range of temperatures, and it has the polarity. We'll talk about that a little bit. Now, as we talk about it, cohesiveness. What is cohesiveness? Cohesiveness is when water molecules stick to other water molecules. Water molecules form hydrogen bonds with each other, and this is called cohesion. And here you can actually see 2 water molecules bonding to each other through a hydrogen bond. This is called cohesion. Now, also, water molecules may bond through hydrogen bonds to other molecules, like cellulose found in the cell walls of xylem. And this would be an example of adhesion. It sticks to something that's not water molecules, okay? Adhesion, water to other things. Cohesion, water to water. Now, because cohesion and water sticks to other water molecules, this creates something we call surface tension. And that surface tension is very well seen. You can see this spider here, and this spider is walking on water, and as you can see, the mass of the spider is not enough to break the surface of water. What this is an example of surface tension. Because cohesion, the water molecules are sticking together, creating a tension or how hard it is to break the surface of a liquid. Water has a fair surface tension to it. In fact, in our lungs, for example, we use a molecule called surfactant to try to reduce the surface tension at our lungs exchange surfaces, something that is used to make sure that we can make the lungs work better. Now, what I want to help you understand next is how it moderates temperature. Now, what does it do? Water has the ability to absorb heat energy. And when it absorbs heat energy, it releases that heat. It basically, you thermally energize water, and it absorbs that heat, breaks hydrogen bonds, and take the hot, the warmer, more kinetically energetic, more energized, more thermally stimulated water molecules leave through evaporation, taking the heat with them. Now, water can absorb a lot of heat energy, a lot of heat, without changing temperature much. So it doesn't change temperature too much, even when it absorbs some heat. Now, let me help you guys understand these terms, because we need to understand the following terms to understand what's going down. Now, first off is to understand when we deal with temperatures, we need to understand kinetic energy, and that is the energy of motion. Now, what I want to help you guys understand is all matter is moving. All matter, all atoms, molecules, they are in motion. They vibrate, they shake, they wiggle, they move about, and they're in this movement. Now, if I want to see that energy that is in a molecule or an atom, we call this thermal energy. The amount of kinetic energy in molecules or in atoms are referred to as its thermal energy. When I measure that thermal energy, that is called temperature. So when I basically, I always like to say that thermometers are just speedometers for molecules and atoms. Now, heat. Now, when somebody says, get over here, give me your body heat. When we heat up food, what are we doing when I say heat? It is talking about thermal transfer. Thermal energy must be transferred. For example, you lie next to somebody, your body heat transfers to their body. Or the hot stove eye transfers its thermal energy to the skillet, and the skillet transfers it to the food you cook when you heat up your food to cook it. Now, these are examples of heat. Heat is thermal energy transfer. Temperature is a measurement of thermal energy. Thermal energy is the kinetic energy of the molecules and atoms, and kinetic energy is energy of movement. So we're measuring how fast molecules are moving. Now, I want to show you this because it really helps me to explain that a little bit from this standpoint. And we could see that as soon as we actually let these guys go, we're going to see, like, let's say a normal temperature. And let's cool it down a little bit. Let's get this kind of cool to where it's liquid water, but it's cold. Let's start getting it more towards a solid. Let's see if we can freeze this down and get the kinetic energy down a lot to forming ice. Now, no matter how cold I get it, it's still going to move. Okay? Now, what if I start to heat this up a little bit? It's going to start to move more. I'm adding more and more heat. The thermometer is measuring the temperature goes up, and the kinetic energy goes up in the system till we have steam. So the kinetic energy is increasing, okay, because the thermal energy is increasing. Something that we need to understand here, okay? Now, specific heat, what is this? This is how much heat must I absorb for 1 gram to change 1 degree Celsius, okay? How much thermal energy needs to be absorbed or even lost to change 1 gram by 1 degree. Now, water has a very high specific heat, okay? Now, because of this, it resists temperature changes. Now, in October, the Atlantic Ocean is still going to be quite warm, which is going to be a peak time for us to have hurricanes coming up. We're basically in hurricane season now. As the air cools off and the ocean stays warm, this creates that unstable kinds of atmospheric phenomena that we know as storms, like hurricanes. Now, these hurricanes, as they go about to increase this season. Now, in April, you're going to have, even though the air's warming up in April, the ocean's still pretty cold. It takes a while to heat up the ocean. It takes a while to cool it down. Now, the heat increase, it takes a lot of heat energy to increase it, like water, to make it vaporize, to make it go as a gas. Now, the heat of vaporization is how much energy does it take to change a gram of liquid to a gas if temperature stays constant. At 100 degrees Celsius, it takes 540 calories per gram to make water boil. At 100 degrees Celsius, okay? Now, that could be easier to achieve at different pressures, okay, at different atmospheric pressures. Okay, now I like to show this. This does a great job. I have a friend of mine who lives out in Riverside, and he might be listening. Who knows? He subscribes to my YouTube channel, so sometimes he'll look at my videos. And he lives in Riverside. And now sometimes he'll trek to Los Angeles. Los Angeles, here at this time, you'll see the Pacific Ocean. So we're West Coast. And the Pacific Ocean being on our west coast in America, 68 degrees. Now, if you're nearby that, you might be very cool, like 73, 75, 72 degrees at places like Los Angeles, San Diego, Santa Barbara. Now, as we move in closer to like Santa Ana, Burbank, it starts getting warmer. Riverside. Now, Riverside and near that area, near Riverside, frequently gets to be well over 100 degrees. As he would tell me, it's 106 outside where he lives in Riverside. And so he'll text me sometimes, let me know how hot it is. And we're like, okay. And then I'll tell him, said, by the way, it's only like 70-some degrees here today. It's nice and cool and dry, and we're liking it right now. And he's like, oh, shut up. So, all right. So why is this happen? Well, it's because you're getting further and further away from the moderating effect of the water. Okay. And that's why. So let's talk about evaporative cooling. Now, what happens when you heat water? It takes a while to heat it up to make it evaporate. But when it does, it breaks the hydrogen bonds. And what you're going to do is evaporation, the hotter molecules, the more kinetic energy molecules are lost, okay? This is the thing. It is the molecules that have the highest kinetic energy who are going to fly off and away, taking that energy with them. That breaks the hydrogen bonds, releases the energy that goes away, and then we're taking away that. This is what sweating does. Sweat is about 99% water, and this helps maintain our body temperature by sweating using evaporative cooling because it is the most highest thermally energized water molecules that actually evaporate. Now, water freezes, it expands. And that also causes it to be less dense. Now, why is this? It expands upon freezing and goes to an extremely stable structure, okay? Now, you guys won't have this, but I do. And it's going to be in my next version of the notes when I teach it the next time. It'll be out there. So I might take this and share it on in our thing, but I want to show it. Is water freezes at the top because it is less dense. Why is it less dense? Well, it's less dense because there are less molecules per volume because it spreads out in this nice, beautiful 60-degree angles and becomes more regular. Now, it is moving, even as ice, just less, okay? Just less. And as you can see that, kinetic energy is different. Now, all right. So what happens is this makes it less dense when it's frozen, which makes it float. It makes it spread out to a more stable structure. This reduces its density, which makes it expand, and also less dense when it freezes, okay? Now, which is I was showing you here. Now let's talk mixtures. We're going to move into another area called mixtures here. Mixtures, they're going to be in three types. They're going to be in what we call a homogeneous mixture, a heterogeneous mixture, and then in biology, I'm going to add the colloid. Now, colloid, we're going to see. Colloid kind of tries to be a little bit of both, and we're going to see about this. But homogeneous, homo means same. Geneous, so the homogeneous means they are the same throughout. This is called solutions. They are chemically bound. So this means if they're chemically bound, it will be mixed thoroughly throughout and the same throughout. Now, heterogeneous, different, means they are not chemically bound. These could be things that could come out of solution due to gravity, things like that. Now, a colloid. This must be large organic compounds in biology. Now, colloids in biology have to be large organic compounds like proteins. Now, things like plasma is a colloid because there are large proteins dissolved partially or somewhat interacting with the liquid, not fully dissolved, but floating in there. And we call them, now it actually acts like it's homogeneous, but really it's actually heterogeneous. They're partially dissolved, one might say. Now, what is a solvent? We said they are homogeneous. Well, homogeneous mixtures solve a solution. A solvent is what dissolves something. A solute is what gets dissolved. So a solvent plus a solute makes a solution. A solution, remember, is homogeneous. It is the same throughout, chemically bound. Now, if this solution in water is the solvent, we call it an aqueous solution, okay? So we're already halfway through, roughly, okay? And we're already through most of the properties of water. Now, water is a great solvent. Now, what I want to help you guys understand is why is that? Well, let's talk about that. Let's say that I have sodium chloride, NaCl, and I add that to water. What's going to happen is it ionizes into its cation and anion. Now, when this happens, what you're going to see is water molecules here. They're going to be present, of course, with the hydrogen's partially positive end and the oxygen's partially negative end. And you're going to see that partially positive end here going to attract Cl minus to it. And you're going to see this partially negative end here attract Na plus to it. And what's going to happen is these other water molecules that are present are going to surround this. Negative oxygens are going to surround there. And positive hydrogens sticking out this way, okay? And then also what you're going to see is, on this side, the positive hydrogens, they're going to come around. Let's do one more here. And they're going to come around, okay? And what you're going to do is you're going to basically act to dissolve it. And what you are forming here is something relatively interesting. Is when this liquid here water surrounds these ions, we call these hydration shells or spheres. Hydration shells or spheres. And they surround it, acting as a method to keep apart the cation and anion. Because what would happen is this cation and this anion would want to form an ionic bond. And if they could form an ionic bond, they would. So what we're going to do is keep this cation and this anion separated using water molecules, okay? And this is called hydration shells. And sorry that when I click on that, for some reason, it does this thing like, oh, you're done, and you wanted to go to the very top for some reason. Now, the negative ends attract the sodium cations. The positive ends attract the chloride anions. This surrounds it in a molecule of water. Molecules of water surround the cations and anions, creating what we refer to, guys, as a hydration shell, preventing the ions from rebonding, causing them to stay dissolved. This makes water a really good solvent because it can dissolve anything that has a charge. If it has a charge, whether it is polar compound or whether it is an ion, water can dissolve it. Water is polar. It dissolves anything that has a charge. So it dissolves a lot of charged substances. Now, hydration shells can even be formed on very large molecules to at least partially dissolve, like proteins, creating that idea where it can be truly actually be heterogeneous but act homogeneous because of the large number of molecules interacting with a hydrophilic protein. Now we're going to know those words hydrophilic, hydrophobic now. What is the word hydrophilic? Hydro water, okay, hydro water. Hydrophilic. Philos is a Greek word that means love. What kind of love? Brotherly love. They love each other like brothers. And if you love them like a brother, you want to be around them. It's like, man, they're like my brother. Okay, it's like my brother. I want to be around them. They're my bros. We're bros, and bros like to be near each other. We're best bros. So the bros like to be in. They like to be around each other. They have affinity for each other. If a substance has affinity for water molecules, it is called hydrophilic. These will be polar, okay, polar, or they also will be called ions. They'll be polar molecules or compounds and ions, okay? Anything with a charge. Now, they may dissolve, they may not. Now, if it does not have a charge, it will not have affinity for water. There's no positive or negative end for me to interact with if I don't have a charge. We're called nonpolar substances, neutral atoms, things like that, are hydrophobic, water fearing. They don't interact with water. Like dissolves like. Hydrophilic is anything that dissolves in water. These are things with charges. Water has a charge. Things with charges dissolve in water. Things without charges don't dissolve in water because like dissolves like. Okay? Suspensions are a type of mixture that cannot dissolve. They're either too big or they are not soluble. They don't dissolve because they're too big, or really they're just hydrophobic or too big. Okay, like whole blood, for example. There's too many blood cells. You can't dissolve the blood cells in the water. They're too big. They're too heavy. Mud. A lot of the chemicals in mud are not water soluble. Things like that. Okay. Now, what's going to happen is, guys, they will settle out due to gravity. We call that settling out, like how it settles, or you can spin it down in a centrifuge, and that makes it a suspension. It's suspended and falls out of suspension due to gravity, okay? Now, something I'm going to talk about is concentration. Concentration is how many molecules are in solution. Now, if we want to figure this out, we need to figure out how much the mass weighs of the molecule. We need to know how much a molecule weighs. And we can measure the number of molecules by looking at moles. Because we could say, okay, a mole is 6.02 times 10 to the 23rd molecules. I have this much that I'm weighing. There's this many molecules. And that's molarity. Okay, we can actually calculate that. Now, I don't have my students calculate it here. I don't even do that in honors. It's something you'll do in general chemistry, and I save it for chemistry for that reason. All right, now I also want to make sure you guys understand water. And water is something very interesting here is going on. Water is just not pure water. Water is actually, guys, a equilibrium between two ions, hydronium H3O plus and hydroxide OH minus, in an equilibrium. Now, the hydronium sometimes gets shorthanded to just H plus, and the hydroxide stays OH minus. Now, these H pluses, H3O plus, which we should know it is actually H3O plus, can actually damage your body's tissues, damage your proteins. So we want to keep them under control very strongly, okay? It's something we really want to control. And we'll talk about how we control that with buffers in a minute. Now, what I want to talk about as well is what happens when we disrupt it. For example, if I have an acid or a base. And we'll talk about that in just a second. And I'm actually going to draw something here. We're going to talk about disrupting this in just a minute. And we're going to talk about what happens when we disrupt it here in just a second. Okay? So let's discuss that and let's talk about it. Now, what I want to help you guys understand is what are acids and bases. Now, pure water is a balancing act between H plus and OH minus. Now, given that, guys, it should be equal in balance. Now, if it's equal in balance, perfect, we can disrupt it. And how do we do that? Well, if I add something to water, and that something increases H plus, we call that an acid. Because it increases H plus, we're going to call these protons. It is now becoming a proton donor. For example, let's say I take HCl and it dissociates into H plus and Cl minus in water. This is going to be counting it as an acid, okay? Now, let's say I put something in water and it lowers the H plus. That would be considered a base. A base is a substance I add to water that lowers the H plus. That is now called a base. So we're going to call them proton acceptors because they lower H plus. Remember, we're going to call H plus a proton. For example, ammonia, NH3, gets added to water. It grabs up the hydrogen ions, forms ammonium ion, NH4 plus. Okay, and now we have an ammonium ion. So it had then gone from a base, ammonia, to forming that, okay? It grabbed up the hydrogen ion, lowered the hydrogen ion concentration, made it a base. Now, loads of things can be acids from this definition of it being what we refer to, guys, as a proton donor as an acid. Loads of things can be bases based on the definition of they are proton acceptors. Now, if you guys are really good with chemistry, you know this is the Bronsted-Lowry definition of acids and bases. You've learned it in Gen Chem, or you're going to learn it in Gen Chem. Some of you are either in Gen Chem now, some of you are already in organic chemistry, and great that you're taking those courses because organic is definitely one of those courses that you can get a lot of good info from it. I really have to say that if there was a course I could go back and retake to help me understand some of the really detailed concepts that I'm now studying myself about what's going on in some of the biochemistry that I'm trying to go now myself and study and understand, is I really need that organic chemistry. Really need to understand that organic chemistry, getting down to that level to understand the really super details about how does things work. And so if there's ever was a class I really wish I went back and got more out of, that would be one of them. That my other classes, Probs and Stats, to be honest with you, those are two courses that I wish I could go back and take now because I feel like I could get so much out of it now. So just to help you guys understand these things, okay? Now, let's talk about the pH scale. It's based on tens. We basically use a tenfold change. Which, what does this mean? It means it is a logarithm. And it is a change. One pH unit is tenfold, okay? Now, we're going to go 0 to 14. Now, actually, you can have below 0. You can have negatives. You can have above 14, okay? But 0 to 14 is a typical pH scale. Now, what we're going to do with this typical pH scale is understand a couple of things here. Big things, okay? A couple big things. First off, what I'm going to see here is, as I'm at 7, we're going to see H pluses equals OH minus. Below 7, we're going to see H pluses are greater than OH minus. And above 7, we're going to see H pluses are less than OH minuses. What you guys are going to see is that a change in H plus is going to be the factor to determine the pH. And I'm going to do this just a smidgen so we can see that a little bit better. There we go. Now, sorry that I'm here in my office, and I hope you guys can't see anything too much. Like, I don't know if I have a note there that shouldn't be seen. I had to move up to my upstairs office today for the rest of the semester, really, just because doing some stuff down in the den. So what I want to do is understand, guys, that if I increase the hydrogen ions, this must mean that I decrease the pH, make that number lower. And if I decrease the hydrogen ions, I must increase the pH. These two things always go opposite. This is a very important set right here. This little box has a lot of nugget to it that you guys can keep with you to have a lot of knowledge. Is when hydrogen ions go up, pH drops, okay? And as you can see here, these are what we refer to as acids. These are what we refer to here as bases. And this is what we call neutral. Now, I'm going to set this aside and come back to it because I'm going to need it. But what I'm getting ready to do is talk about how do we figure this out. Well, we need some math. And I'm going to do it this way. The concentration of hydrogen ions is equal to 1 times 10 to the negative pH. 1 times 10 to the negative pH, okay? So, case in point. Let's say I want to know what the hydrogen ion concentration is for a substance with a pH of 1. Well, before we do that, let's do this. What is 1 times 10 to the 0 power? Well, that is 1.0. Very important that we know that. Now, let's take this and do our equation here. 1 times 10 to the negative 1. How do we figure that out? Well, what you do is take 1.0. That's our starting point. Now, just like in lab, there are two things you're going to see this negative value tells me. Number one, this tells me that I am going to the left. Negative says the decimal is moving to the left. 1 tells me how many times I'm moving it. So I'm moving this decimal 1 place to the left. 0.1 moles per liter of hydrogen ions. Okay? And what if hydrogen ion concentration in this case is for pH of 2? Again, 1.0 is our starting point. We're taking this decimal and moving it 2 times to the left, 0.01 moles per liter. And let's just really jump. Let's really jump. H plus concentration 1 times 10 to the negative 8 power. That means a pH of 8. 1.0. What do we do? 8 times to the left. 1, 2, 3, 4, 5, 6, 7, 8. Decimal. Fill in the zeros. 1, 2, 3, 4, 5, 6, 7. So 0.1, 2, 3, 4, 5, 6, 7, 1 moles per liter. Now, what you're seeing here is mathematically, logarithmically, me proving to you that if I increase H+, this equals a decrease in pH. And if I decrease H+, this equals an increase in pH, okay? Anytime that we go up in pH, you're dropping your hydrogen ion concentration, okay? Simple as that. The highest would, of course, be 1 mole per liter. As we get 10 less. It's a tenfold change every time, okay? Be able to do this calculation. It's not that hard, but be able to do it. There'll be at least one question on the test where you'll have to do it, at least one. Okay, maybe more, but at least one. I usually do 3 pH questions at least. So here I've done the first 7 for you. And what I like to do is I should say 1 times 10 to the negative pH to make it easier. Because to me, it makes it easier doing it that way. All right. So again, acidic is anything less than 7. That means H plus is greater than OH minus. Neutral, pH is 7 and 7 only. That means H plus is an OH minus equals. And basic is anything greater than 7. That means H plus is less than OH minus. Know these relationships. This will help you guys in generally knowing. Like I could always give you a pH range and ask you guys which of these is most acidic, most basic. Things like that. Which of these has the highest hydrogen ion concentration? Which of these has the lowest hydrogen ion concentration? Understand this relationship. Okay. Typically, I kind of give you an idea that I like to ask things like, what are proton donors? What are proton acceptors? Which of these is most acidic? Which of these is least acidic? What is the hydrogen ion concentration for a substance with a pH of blank? What is which of these have more or less hydrogen ions, those relationships. Be able to understand that. As we said, acids donate H+, bases donate OH. They also accept hydrogen ions. Now, I'm using H+ in my definition. I'm sticking strictly to Bronsted bases and acids. I don't want to go into Lewis acids and bases that deal with electrons. I want to deal with the other thing, okay? Cool beans. Cool beans. And you can see a few things here. Now, like I said, lemon juice is actually quite a bit acidic. People sometimes will say like acidic, but it's 2. And people would say it and they're trying to say they're alkalining their body. Lemons are acidic. You're not alkalining your body with it. And you're not making your body more acidic either. It is very wrong to think that. If you can eat something and change your body's pH that dramatically, you need to see a doctor now. You have a problem. Now, very common things that we use in our body, like blood is actually about 7.4 on average. 7.4 pH is human blood. Human blood ranges between 7.35 to 7.45 in human blood. But a lot of things tend to be a little bit weakly basic. Pure water, and now human blood, as I said, 7.35, 7.45 is actually the range. 7.4 is the average pH of human blood. Do not have to memorize that. In A&P, you better. If you take me for A&P, you better memorize those. All right. Now, what is a buffer? Buffers are something that keeps our pH balance under control. It is what prevents dramatic changes. Okay? So let's explain it. We want to be, if you're in biological systems, you want to be very close to 7. Like blood is 7.4. That's quite close to 7. Now, small changes can kill you. If you get below 7.35, you can die through an acidosis. If you give it above 7.45, you could die of alkalosis. And that can kill you. Now, here is something that I find very fascinating. If I take acid, like some vinegar, and I put it into pure water, the pH goes pH goes down quite a lot. Hydrogen ions go up quite a lot. But if I add it to blood, there's very little impact. And why that is water does not have buffers. Blood does. The buffers minimize the change. And what buffers are, they're always a acid-base pair. It's a weak acid, a weak base, and that can reversibly combine with hydrogen ions to be able to minimize the changes of hydrogen ions. By far the most important one is called the bicarbonate buffer system, where bicarbonate HCO3 minus bicarbonate ion is a weak base. And that weak base is one of the most important ones we use. Treatment for bicarbonate is heavily used in treatment. Bicarbonate is produced as I hold my breath, CO2 reacts with water. That forms carbonic acid. The carbonic acid actually dissociates. I have found that I am missing this right here. And when I started, Dr. Osborne got so mad anytime I ever had these arrows like this. I was like, it won't do it. And he said, well, there is a software that lets you do that. It's like, it's not compatible with PowerPoint. So I always write it like that. And I'm sorry that I had that typo there, and I'm going to fix it and save it because I like doing that. All right. This is the part you can put your pencils down and don't have to worry too much. I don't test on this. This isn't on the exam. But I do want to mention that climate change is a really serious issue. I mean, by now, NOAA, NASA, a lot of our most important scientific associations who are responsible for studying this have all agreed climate change is real, and we are the primary cause behind it by burning fossil fuels. And it's almost unequivocal now, to the point that I used to be a fence sitter about it. I agreed that it was happening, but I was a little unsure to what degree humans played a role. That was probably about, say, 10 years ago. And since then, I have come off my fence because I always believe if you sit on the fence, you're likely to be impaled by it. And I definitely have unsat off the fence. I'm sitting in the pro that climate change is primarily human caused camp. I'm just going to go ahead and put it out there. It's not political football to be played with. But what happens is CO2 gets out there. CO2 happens to be a important what we call a greenhouse gas. Now, but other ones out there, for example, is sulfur oxides, nitrous oxides. They also come from that. They come in and form like sulfuric acid, nitric acid. They form these acids in the air and come down as rain and snow, or even fog, acid rain, acid snow, and acid fog, and their pH is less than 5.2. So quite acidic for something that falls out of the sky, which is enough to harm life. Now, CO2 can also dissolve in salt water, making it acidic, and the greenhouse gases coming out, warming it up. And we're seeing this acidification, and warming is wiping out corals, destroying the calcification of corals, killing the corals because they can no longer live with the chlorozorelli and zooxanthellae, which are symbiotic organisms they must live with. They get jettisoned, they die and starve. We get coral bleaching, and then the corals actually get taken over. Healthy coral don't have algae and things growing on it like you will see in bleached out dead coral. And we can actually see these things like CO3 2 minus bicarbonate ions here being measured, and we can actually see that that calcifications here are being affected with this. Okay, so it is affecting the coral. It is beginning to take away like calcium carbonate, which they would use. The bicarbonate ions are getting shifted with this chemistry. Le Chatelier's principle is resulting in loss of carbonate production. And it's actually the calcification is being taken out of the coral, damaging the coral because the chemistry is disrupting the chemical equilibrium of the coral reefs. Okay. This is a great video to watch. I'll urge you guys to go watch it. I'm not going to play the whole thing. It's too loud or too long. But it's a great video. I know it's a little bit older, but it's a great video. Goddard and some other places may have some more new ones out. But I think this, amongst a few others, are great examples. If you are looking at research on climate change, if you wanted to do your paper for honors, climate change is a great one to do. Speaking of that, for next semester, for spring, I have great news just today, right before I recorded this, because this is why it's 7-something now before I'm finished, is I had just finished communicating with a contact at Virginia Tech and at Virginia Tech. He wants to collaborate with us. We're going to help Virginia Tech at a nearby site, nearby the campus, very convenient for us to be research partners with Virginia Tech to for us to go out and be research partners with them. So, which also means if you're interested in Virginia Tech, we have some connections for you that we're going to be building up. And I think you guys I'm super excited for this. I hope you guys are too. I'll talk about it in lab on Friday as well. But guys, I think we'll see some really awesome things coming up. I don't know how soon it will be. If he gets to want to have a meeting soon, I'll be in communication with you guys, and we'll go ahead and get started with that, okay? So, guys, this concludes my video. I hope you guys found this a very useful and engaging lecture. Thank you guys so much. Always glad to be able to teach you guys from any way that I possibly can. But this concludes my video, guys. Thank you so much. We'll see you in the next one.